Welcome. In this explainer, we are going to dive deep, and I mean really deep, into the very heart of gypsum board. We're going microscopic to figure out how to engineer superior performance, basically, how to build strength from the inside out. Okay, so here's our game plan. We'll kick things off with a big lightweighting challenge. Then we'll zoom right into the gypsum core itself. After that, we'll look at two key solutions. First, engineering the perfect void, and second, building a stronger matrix. And finally, we'll see how it all comes together. All right, first up, let's frame the fundamental problem. You know, the one that keeps every gypsum scientist up at night. This right here is the central conflict, the big paradox we're all fighting. The market is demanding lighter board that's easier to handle, easier to install. But, well, the laws of physics are pretty clear. When you take away mass, you almost always take away strength. Our job is to find a clever way around that trade-off. And this is where the rubber meets the road. As we chase that lower density, the one metric that really takes a hit is nail pull resistance. And this isn't just some optional feature, it's the critical performance measure. It's governed by standards like ASTM C1396, and it's what tells you if a screw or nail will actually hold. It is our ultimate test. So now, let's zoom in. We're going to go from the big picture of the board down to the microscopic level to really get a feel for the battlefield we're on. Okay, first things first. You have to stop thinking about the gypsum core as just a solid slab of rock. It's not. It's what we call a cellular solid. It's basically a foam. Think of a honeycomb or even the structure of bone. What that means is that its strength doesn't just come from the gypsum itself, but from the architecture, the specific arrangement of the solid parts in all those empty spaces. And this slide just lays it out perfectly. The difference is night and day, isn't it? On the left, that's our goal, a beautiful, tight network of small, uniform bubbles. It's strong, it's predictable. But on the right, that's the enemy. Random, huge voids that act like giant potholes in the structure. They concentrate stress and are just waiting to fail. This quote, "This is everything." It's a fundamental rule for materials science, and for us, it's our guiding light. It tells us exactly where to focus our attention. It's not the average bubble size that matters most. Nope. It's the biggest one. That single largest flaw is the weak link in the chain, and it's what will ultimately decide how strong our board is. So, how do we measure this largest flaw? We use a metric called D90. Think of it as a way to quantify our main enemy. This number represents that coarse fraction, the biggest 10% of voids in the core. If we can get our D90 down, we are directly attacking the #1 cause of nail pull failure. It's that simple. Now, this equation, the Gibson-Ashby power law, might look a little intense, but it's basically our rulebook. It's the physics that connects the board's density to its strength. Our real goal is to engineer that little exponent n. See, what we want is the lowest n value possible. A lower n means that as we make the board lighter, its strength goes down much, much more slowly. So all this work on microstructure, it's really all about getting that n as low as we can. Okay, so we know the problem is big voids. Now let's talk about our first major strategy, actually engineering the voids themselves. We're going to turn those weaknesses into strengths. This is where things get really cool. Check out this phenomenon called the wall effect. This is where the gypsum crystals themselves form a dense, reinforced shell right around the air bubbles. So now, instead of just being an empty weak spot, that void becomes a rigid, hollow sphere. We are literally turning a defect into a structural load-bearing part of the board. So what's the catch? Well, the manufacturing process itself is incredibly hostile to our perfect little bubbles. The intense shear forces inside the mixer are trying to rip them apart, causing them to merge and form those big, ugly voids we hate. So our solution is to play defense. We have to stabilize the foam, basically give the bubbles a suit of armor so they can survive the trip. And we have two main ways to build this armor. On one hand, we can use some pretty sophisticated surfactant chemistry. Think of this like creating a flexible, almost self-healing shield around the bubble that can stretch and absorb the forces. On the other hand, we have what's called Pickering stabilization. This is more like building a rigid suit of plate mail. We use tiny particles, like starch, that physically stick to the bubble's surface and create a solid barrier. All right, let's move on to our second big solution, because it's not enough to just perfect the voids, right? We also have to strengthen the solid stuff in between the voids. and that is all about the gypsum crystals themselves. You know, the actual shape of the gypsum crystals is a huge lever we can pull. On the left, you see those long, thin, needle-like crystals? They're like a pile of toothpicks. They don't pack well, and they buckle really easily under pressure. Now look at the right. That's what we want. Short, stubby, blocky crystals. These are like a wall of bricks. They pack together tightly and are way, way better at resisting being crushed. So how do we get from toothpicks to bricks? The secret ingredient is a chemical trigger called succinic acid. This little molecule is a total crystal shapeshifter. It works by latching onto one side of the growing crystal, stopping it from getting too long, and forcing it to grow wider instead. And just like that, you get that strong, blocky shape we're after. And what's the payoff for all this chemical magic? Look at that number, over 40%. By changing the crystal shape from needles to blocks, we can boost the compressive strength of the gypsum matrix by more than 40%. That is not a small tweak. That is a massive gain in performance. Okay, for our final step, let's put it all together. We're going to combine these two incredibly powerful ideas to see how they create a truly top-tier gypsum core. And this is the main takeaway, really. It's not an either-or thing. You can't just have a great void structure and a weak matrix, or vice versa. The real magic, the true high-performance board, comes from the synergy of both. A perfect lattice of small, armored voids, all held together by a super strong, crush-resistant matrix of blocky crystals. That's the winning combination. So, we've walked through the cutting edge of what's possible today, controlling both the empty spaces and the solid stuff. And that really just leaves us with one big, exciting question, doesn't it? What's next? What new chemistry, what new process is out there waiting to be discovered that will unlock the next level of control and give us the next big breakthrough in performance?